Hey everyone, this is Bathmetrics and welcome to episode 11 of GridSchool for Bitwig 3.0. In this video, we're going to be talking about the first practical application of all the basics I've been teaching you in the previous episodes. We're going to talk about how to gate things or effectively activate or deactivate things depending on the incoming audio signal. This is a really useful technique you're going to use all the time. So before I continue, just a reminder that every episode of GridSchool I do builds upon concepts and techniques I've showed you in previous episodes. So if you're just dropping in now here on episode 11, please be sure and find my GridSchool playlist and maybe consider starting with episode 1 and working your way up to where we are now, because trust me, it'll really help. I'm just going to be talking about all kinds of terms and concepts that you may not have been exposed to yet. Okay, so the basic problem today is that when we have been talking so far and demonstrating what the grid looks like, we've been using a polygrid, and polygrid is basically for building synthesizers and instruments, and everything that happens in the polygrid is pretty much controlled by incoming note gates. Right, so here we have a gate that isn't hooked up to anything, just to show you what the normal input would look like, because most of the devices that are triggered by gates have this handy little precord here that you can turn on or off. So if I have this precord turned on for the envelope, we hear something every time I press a key. This oscillator is always free running. So let's just briefly show that by hooking up an oscilloscope. See that oscillators are always putting out some type of signal, and you have to use a gate to shut up that signal unless you want to hear it. But it's always free running, okay? So the problem is, what if you're using an audio grid, an FX grid, my bad. I think of it as audio. And you're trying to process some type of incoming audio signal. So here, what I'm doing is I'm playing a little sub-bass patch set up in polysynth, right? And from this polysynth patch, I want to apply some effects to it. So here's the bass by itself. And here's some effects being added to it. So how do you do that? How do you make an effects grid, which is what we have right here? How do you make this react only to incoming sound? And it's the incoming sound that triggers whatever's happening inside the FX grid. There's nothing in here that's reading my note gate. Right? I could, for example, be playing this drum loop. Now it'll sound strange because I set up this drum loop for a different example we're going to talk about in a few minutes. But just to show you, you're going to hear a little white noise, maybe. Let's see. Well, you can't really hear it over that drum loop, but every time the drum sound is hitting a certain level of volume, it's triggering what's happening in this FX grid too. So let's talk about how we do this. It's a lot easier if I just manually trigger some instrument like this sub bass, so you can clearly hear this white noise signal that's being triggered every time I play. That's being added to the sub bass. Sub bass alone, sub bass with the white noise. And it's only being triggered when audio comes into the circuit here and is high enough, and we process it a certain way to be able to successfully trigger on and off everything else that's happening, which is this purple row that's creating all the rattlesnakey kind of white noise layer. So, just adding a little bit of texture to the to the sub bass, so it has some stuff going on in the high end of the spectrum. So the key here, the trick I'm showing you today, is the stuff in green. This is the standard pattern that I would recommend for setting up your audio detection gating. And you'll notice that the sub bass is going straight through from where it comes in to the FX grid device and then straight into a mixer, and we're not modifying that signal in any way. Then we're using this green section to do a little bit of detection gating, and it terminates in a logic module, specifically the one called, what do they call this? They just call this the equals or roughly equals module because it's that sort of tilde equal sign, not a straight equal sign. And it terminates in that. And then from here, we're going on and we're triggering some other mixers that are triggered by logic or another logic thing to make certain things happen or not happen. And then the stuff that happens or doesn't happen, depending on whether audio signal is coming in, is being fed into the mixer and blended with the base signal. So let's talk about what this is doing and why we need all this stuff, okay? I'm going to use just the white noise trigger for now, just to keep it simple. Actually, let's use the bass. So in this case, the problem is incoming audio signals, if we were to look at them in a oscilloscope, I'm going to hook an oscilloscope up here just so we can see the incoming sub-bass audio. Okay, here's the problem. See how the incoming audio waffles around above and below zero? Because it's a wave, right? If I slow this down a little bit, you can see it. You know, this is the actual sub-bass signal, both sides of zero. Now, the problem is, if you're trying to trigger logic from this, remember, logic always operates on everything from 0, the center line, to 1. And as you get above 50%, you know, once you're above unipolar 50%, that's when logic gates trigger into true mode, right? Any signal from 0 to 50% is false, and logic gates don't even listen to any negative signal, right? So logic gates are a unipolar signal from 0 to 1, and they only trigger true when the unipolar value is above 50%. So when you feed a raw audio signal into something that's trying to detect is there audio or is there not, if you're not doing something special to flip it all positive and keep it pushed up nice and high, your logic gates are going to keep flipping on and off. And so that's really confusing. So the trick we use to get around that is to add an envelope follower, which is one of the envelope groups right here. By default, it's this color. And what an envelope follower does is it averages the incoming signal, and it also flips it 100% unipolar. So what I'm going to do now is connect the audio follower to the same oscilloscope, but we're going to play a little game just to see it better. And I'm going to grab a gain dB value and stick it right here. This is neutral. I'm only using this so I can change the color. All right, so the green signal coming in is the original, and you can see behind it there's a purple signal that is the signal coming out of the audio follower, right? If I turn off the purple signal by just disconnecting it, that's what the audio follower signal looks like. See how it's all positive? And then normally, and I do say normally, if we were trying to use this signal straight out of the envelope follower to trigger logic, this line would have to be above the 50% mark to actually trigger logic. But we're not quite doing that sort of comparison. We're instead taking the output of the audio follower and we're feeding it into a level scaler device, which I think is, where are you hiding, Mr. Scaler? No, level? Yeah, it's a level device. So we're taking the audio level that's coming out of the follower and we're scaling it way, way, way down. We're basically saying we want you to take whatever signal's coming out of the audio follower and make it no louder than negative 40 dB. And it can go all the way down to the floor at negative infinity. So it's just, we're just constraining the range of this audio. We're pulling it way, way, way down, because what I'm trying to do here with this last comparison is say, I want to know if the signal coming in here and flowing through this signal path Is it equal to 0, like nothing, like infinity, negative infinity? Or is there some amount of signal? And I want only a really small amount of signal difference to be detected here. Like as soon as signal comes in and it flips somewhere closer to negative 40 and is therefore no longer equal to 0, you can watch this light turn off, which means it's false. Because right now, there's no signal, so the amount coming in here is equal to here, which is 0, since nothing's hooked up to it. So 0 equals 0, which means this logic is gate is true. But the minute some sort of signal comes into here, and this top port is no longer equal to 0, then this becomes false. And that's why it turns hollow. Okay, now before we go on, let's talk about how to set the follower settings for audio detection. Typically, you don't want any rise time because that'll take too long to finally get up to a high level, right? You want it to instantly trigger on, so you want the shortest rise time possible. What you do want is a long fall. If I drop the fall time down to very short, you're going to see that the signal coming out of the follower excuse me, looks pretty similar to the original audio signal, except it's all unipolar. But see how it jumps up and down? It's going from 0 to 1 to 0 to 1 to 0 to 1 really fast. If I change this to try and show the pitch, you'll see that it's bouncing, and it's often hitting 0. It's flipping around between here and here. And you can't have that for audio detection gating. You need to smooth this out and average this out and make the line just go up and stay up. It can jiggle around a little bit, right? But as soon as I, make the fall too short, it starts bouncing close to 0 again. If I push it up just enough that it's kind of stable, maybe wiggling a little bit, that's effectively what you want coming out of the audio follower. And you can get a little visual representation of it right here. See, it goes up and it stays up. It goes up and it stays up. That's what you want. And the reason I have these two VU meters here, which are part of the display group, right? You can add these in. It'll become a little more apparent in the next example I show down here, but a lot of times there's a lot of bounce and wiggle, and your volume may be really rapidly jumping up and down on the original signal that's coming in. This sub bass is pretty even. There's not a lot of dynamic range to it between peak and RMS, but you kind of want to be able to see if you're jumping around a lot, and you want to make sure that your audio follower has smoothed things out enough that the second VU meter just goes up close to the top and stays there. Now, the other reason I have a gain control here is because you need a certain amount of level to get this line far enough up coming out of the follower. You need the signal kind of close to the top, but not necessarily peaking into the top. So depending on your incoming signal, you might want to make it louder or softer as it goes through this detection circuit. Remember, this gain is not affecting the actual gain of the sub bass coming in, nor is it affecting the gain of the thing we're merging with the sub bass, the white noise signal that we're mixing in. Instead, it's only affecting how strong the detection circuit is, and specifically how strong the value coming out of the follower is. So if you set up a little volume knob like this, it's your choice whether you want to put in a VU meter here on the input or not, but you definitely want this VU meter because for this kind of detection circuit to work well, you want to make sure that you've got, your smoothed signal up, in the 80% range or higher, close to 0 even. See how this is probably at 90% VU? That's what you want it, close to the top. And if you've got your incoming signal set so that it's close to the top after it comes out of the follower, and that you're seeing the line just go up and stay up like you see here. And again, if I slow this down to show the actual waveform, it doesn't look solid, it looks hollow, and there's just a line that goes up and stays up, right? Again, if your fall's too low, that's the wrong kind of signal. That's not going to trigger a gate smoothly. You need it to be a smooth line that just goes up and stays up, right? So a signal like this is what you need to effectively do the final comparison, which is, all right, have I got any sound at all coming in? It's either here in this state, which is 0, or it's up and it's not 0. And the last thing to know is, why do we use a level scaler at all? If you crank this up, and basically say the level can be anything between -infinity and full 0 dB at full scale, this can still work, but a lot of times it makes the comparison stay active for too long when it falls, because there's a fall time over here. Look at this little graph and see how it has a curve. It has a fade out on the fall. We have to push the fall up in order to get the signal to just come up here and stay up here. But then when you let go of the incoming signal, when it stops, it takes a few milliseconds for that signal to finally fall back close enough to 0 to trigger this and effectively say, yeah, you're pretty much 0 again. So the reason we use the level scaler and set it to, I like -40 as a general rule, is this way, even though the follower is taking a few milliseconds to finally drop the signal back down close to 0, this has scaled everything down so that it's barely above 0. Check it out. If I take the output of this and run it into here, see how the line doesn't even go up? It's like you can't even see on the oscilloscope that it's above 0. Maybe if I crank this up a little bit. Yeah, see, it's like even with plus 24 dB, you're barely seeing the line wiggle. See how there's a little bit of wiggly in there now? So see, the level scaler is tricking us a little bit, because it's basically saying, yeah, push it up above 0, but only the tiniest amount, like so tiny you can't even see it on this built-in oscilloscope in the grid, unless you really amplify it as much as you can. See, now we see the tiniest bit of jitter or wiggle here. So this makes it the difference small enough that it basically instantly falls back to 0 when you let go of the key, because it's already so close to 0. That's why we do this trick. So that's a really important thing to remember as we go forward. So let's get rid of this, and let's show you how the rest of the logic in this particular example is working. This is the key, though. This set of things, you can make something like this and save it. You can make it and take a screenshot of it and just file it away for yourself, or keep it in a preset that is basically just this and a mixer and the output and then this detection circuit, and you can just sort of, have this ready to go. So again, the basic idea is when signal comes in, this final comparator evaluates from true to false, and that's triggering two different things downstream. The first thing it's triggering is whether or not this white noise signal is coming through at all, and we're doing that with a select device. So right now it's true, which means the select is using the bottom channel of the select mixer, right? This is a binary A-B mixer. It's either on or off, one channel or the other. And the incoming channel that's associated with the true condition has nothing coming into it, so there's no sound. So we've muted this white noise generator over here. And again, white noise, like all generators, is always running, right? So we need to keep it quiet or it would drive us crazy. Okay, so when this finally turns false and it comes to the select, that flips the signal up to the false circuit, which is the top channel, and it lets the white noise come through. So then we start hearing the white noise. So here again, if I push the level scaler up, I'm going to press the key and let go. Let go. See how long it took? There was a delay. Press, let go. See how there was a lag before it finally switched back down to 0? That's why we make this value smaller. So that, let go, let go, let go. See how it instantly drops? That's why we need this level scaler at the end, because it kind of overrides the longer tail fallout on the envelope follower. Okay, so this is what's letting the white noise pass through or not, but we're also doing another fun thing with this detection circuit, and that is we're triggering a short one-shot AD filter on this low pass filter that's affecting the white noise. So we get a little bit of a sharp increase in the filter value, and then it drops back down to where it's set at. So if you listen really closely, and I'll turn this up a bit now, it's pushing up and then dropping down. And I could make that more pronounced if we want, so you can really hear it. I just want a little bit of an extra transient there, though, so I'll put it back where it was. So the way this works is, by default, when everything is silent and there's no signal coming in, the outcome of the detection circuit is true. So we don't want a true signal triggering the envelope and keeping it open. So what we do is we use the logic module called not, which basically takes anything that's true and flips it to false, or vice versa. If a signal coming into this were false, it would just automatically flip it to true. So see here, we want to use the true-false circuit to do one thing. Here, since by default what comes out of the detection circuit is always true when there's no sound, we need to flip it to false to keep this envelope quiet and not do anything. So even though you see a white dot here, it's just already at the end of its thing and has stopped. And it's only when we let signal come in that it triggers the gate finally. And of course, to do that, you probably want to turn off the pre-chord so that if you're actually pressing something on your keyboard to trigger the sound that's coming into this, it's not hearing the gate of the keys that you're pressing on your keyboard or MIDI controller. So we want to turn this pre-chord off for a circuit like this. And now it's going to respond only to what comes out of the logic in front of it. Okay, and then the other thing that's happening is just a very simple oscilloscope. I'm sorry, LFO. I was looking at this. Is an LFO that's just sitting here. It's not physically connected to anything. We're just using the wireless connection here to take the outcoming white noise signal and keep flicking it back down to 0 with this attenuate knob, which is in the level group right here. Right. We're using this square wave type of LFO to just like flick it down to a really short duration, binary on, off, on, off, on, off. And if we were to look at it with the oscilloscope, let's put this here and let's connect this to it instead. Well, actually, not that one. That's the oscilloscope itself. Let's connect this one. And now you can see it's blinking on and off a lot. If I flip it down to slow, well, let's try fast. There, see how it's doing this rattlesnake kind of gapping? This is what we're actually hearing for the white noise. And it's just constantly flicking attenuation all the way down to 0. If I were to make it less attenuated, we'd start seeing something like this with a little constant white noise floor. And then, with the length of this, you can make it really gappy, or you can make it each of those things fatter. You can almost make it a sputter, almost like the sputter in Erosion from Ableton Live. It's not quite the same, but sounds similar. So that's a few tricks for using a audio detection gating circuit. It's just the green thing, and then you can use this logic thing at the end to trigger or not trigger anything you want, and it's always going to be responsive to the incoming audio. Now let's flip over to one more real-life example. We're going to go to this one now, and I'm going to select this and activate this circuit, and we'll open up this grid. So here, we have the same basic circuit right up to here. And then these two have been added on as a little extra thing. Okay. And what we're doing here is we're using this audio detection gating circuit, same exact one, to trigger something that's hiding down here in the post effect slot, which is Hornet's the normalizer. So this is a weird one. It could be anything. I actually built this for polarity because he did a great video about using the normalizer, but he was sad that there weren't ways to make it sort of like automatically respond to incoming levels and automatically turn itself off. So, I said, well, we could use the detection circuit for that. And if there's no signal coming in, we can actually turn off the normalizer. And if there is signal coming in from, let's see, let me do it this way. Select you and do Shift D to open up just the floating window. So I've got these drum loops, and when the drum loop is playing, it's going to use this little part right here to turn on the normalizer and let the normalizer do its thing, which is constantly normalizing the signal to a certain value that you want. Okay, and when the signal stops, the normalizer turns off. And in this gap between the two clips, it's also going to turn off. So watch this button here as it hits the end of the first clip. See how it turned off? Then it turns on again instantly. And then it turns off. Okay, so what's happening here is, same detection circuit. We've adjusted the gain to get the right behavior we want coming out of the follower. Scalar is exactly the same. The final comparison is like, is there sound or not? And then that's just triggering a simple, we're turning this constantly positive or true value. We're turning it to false when there's no signal. But then when the false is finally triggered into true and this turns solid, then we fire a modulator, and this modulator is connected to the on button. So whenever this becomes true, this modulator turns on the on button of the normalizer. And then when sound stops and this finally evaluates to false at the output, then this turns the button off. So you can watch. As soon as sound comes into this, you're going to see this go false, which means this goes true, which means this goes true, and it's basically like modulator on. And then when I stop the sound after a few milliseconds, you see it go false again. And so this is controlling the on button. And then I stop sound and it turns off after a second. Now, in this case, I didn't want it to instantly turn off because an audio clip could have some tail to it, like a reverb tail, or it could just be slowly fading out. You can even see at the end of this drum clip, the final kick takes a little while to fade all the way out to 0 at the end of the clip. So I didn't want this to instantly slice off the normalizer. I wanted it to have a little bit of lag in there. So, again, to do things like that, you might play with the gain to get the kind of behavior you want over here and out of the level scaler. So this is the important thing. And now I want you to watch these two meters and watch the huge difference between what this meter is doing versus what this meter is doing. Right? So this is the incoming drum hits, and you can see they go really loud and then down to almost 0. Like bouncing up and down all the time in the gain, but you need to smooth that out and just turn it into something that stays high all the time to trigger the rest of the detection circuit. You'll also notice that in this one, I used the RMS value instead of the peak value to be the thing that's normalized. I don't want every one of these transient peaks to be the thing that I'm normalizing and averaging, if you will. I want the the overall energy, the RMS, the non-peaky stuff. So I'm taking the non-peak stuff and really pushing up the follower's fall time. And I have to do that to keep this line up above 0 long enough to keep this smooth and steady. So again, if we pull out an oscilloscope and take a quick look at this one, the outcome of the follower. See how the line basically goes up and stays up away from 0, which is what we need for the rest of the circuit. And you'll notice that when I finally stop the clip, it takes quite a long time to finally drift back down to 0. That's because of this long fall time, which is about 400 milliseconds. And I find that you don't usually need much more than 400 milliseconds, especially if it's on the RMS. 400 milliseconds is about the window for an RMS measurement in the first place. So it's got a fairly slow decay down to 0 that will finally turn this circuit back to true. And that's why there's a little bit of lag before it turns off the normalizer. Now, if I wanted to make it turn off the normalizer more quickly, I would adjust this value downward a little bit so that this dropped faster. See how the normalizer turned off instantly? Watch this again. And it just instantly turned off. Well, we don't want that. And we want to make sure that the signal stays high enough above 0 to trigger the detection circuit. So, sometimes just literally the difference between 100 milliseconds and 400 milliseconds will make all the difference in how this detection circuit is behaving and staying open and, triggered, and then finally shutting off. So you have to play with the difference between gain. Like the drum signal here is super loud, so I turn down the gain because at 0 it's just like, peaking up this meter and then keeping this one super high too because it's just so much signal. So sometimes you need to adjust your gain to keep your input like close to 0, peaking close to the top, but not at the top or over the top. And then you adjust your fall time to determine how smoothly and consistently the average envelope signal stays, well above the 0 line. And doesn't get too close to the 0 line in the gaps between some of the sounds, right? Like see this little gap right here. It was drifting down close to 0, but not quite 0. So because it didn't quite hit 0, it never triggered this one to be false again, right? So I think if you play with this general idea, again, it's all about this circuit right here. If you play with this general idea and experiment with a few use cases, you'll have it, burned into your brain pretty quickly. But this is the trick. I spent a lot of time trying to figure out how do I make FX devices, really smoothly and predictably respond to whether or not there's any signal coming into them or not. And this is the answer right here. Hope this has been helpful. I'll see you in the next video. Bye-bye.